Okay, hello everyone. So this project is about to model a vehicle with 7 degree freedom, 7 state, to avoid 2 obstacles. So that is the big goal. So let me show you. We're gonna model the vehicle using the magic formula, Pacejka formula, that we gonna read from the Firefox CSV file to fitting the B and C parameter values, and then we use us to find the formula for to calculate the tie force for the front wheels and the rear wheels, and from that we're gonna write a function for the vehicle dynamics that receive the state and the control using the magic formula, and then we have 7 state here. X, I, V as the lateral speed, R is the yaw rate, C is the yaw angle, UX is the longitudinal speed, and delta F is the steering angle for the front wheel. X is the accelerations, and the delta F is just the steering rate, and alpha F and alpha R is just slip angle we need to calculate to use for this magic formula. And then we're gonna write a state propagators, which is simply an explicit forward Euler to calculate the next step, for the next state, and we will try to simulate the vehicle in this file to check whether we are in the right path or not. So let me show you. This is the forward Euler. So you can see the time step that we use to pass in the forward Euler does matter in this case. So we need to set it small enough so that it will create make a good simulations. So let's see the obstacle avoidance here. So in this problem, we wanna formulate with the initial conditions the upper bound and lower bound state, and also we constrain the control input as well. And after that, we using the if-op library in the UMP library, built libraries in Julia, we set the number of states, we set the number of controls, we set the prediction time horizons and the point, and after that we use this prediction horizon time to divide it by the time step we want to simulate to calculate the number of column points, and we set we constrain the variables, and we fix the initial conditions here, and because we use the direct transcription method in optimal control, so we gonna enforce the vehicle dynamics as a constraint here, as you can see here, which is the backward Euler method here. And after that, we gonna write the cost function for each of the term here. So we want to try for the lateral. We try to maintain the lane keeping by setting this one, it's just y -0 here square, and we set the cost weight. This can be tuned of course, and we choose the block list, which is the obstacle here. They're going to be 2 obstacles here, so if you want to increase the number of obstacles, simply just expand this block list matrix. So it's going to be defined, it just simply defined with the first element, is just the x value and y value and the radius of the obstacle, and we have the simple function cycle shape here to plot it later. And after that, we set the constraint to avoid the obstacle here. I think you can understand this slide. And then we set the objective, set the minimum, choose minimum, we optimize the model, and we retrieve the data back to the state history, and after that we just plot everything out to see. So now let's see the output. Okay, so you can see here the vehicle try to minimize the deviations from y equals 0 with the original length, right? But at the same time, it try to avoid two obstacles which are put in position in coordinate 32 and 60 minus 2 here with different radius. One has radius 6. You can see there's one small circle, and the other we have another big circle here with radius 7, and it try to avoid two obstacles while try to maintain minimizing the deviation between the lane keeping. You can see it touch the tangent, slightly touch the arc of the obstacle. So yeah, that's it. So yeah, thank you for watching.